Look here. In this project, we train a convolutional neural network to predict global parametric transformations to redirect visual attention inside an image. Photography professionals regularly edit photos to change the focal point or to enhance or downplay an image region. We ran some initial studies with professionals using familiar tools to study common operations. Here we see some common image editing operations applied to make the center bison stand out. Lessons from these studies show that when adjusting a photo's focal point, professionals preserve image semantics by restricting edits to parametric transformations, and more frequently than not, they apply separate sets of transformations to the target object and the image background. What if we could achieve the same objective automatically with a click of a button? Notice how the car has become more attention-capturing without major modifications to the rest of the image. This is an automatic result from our approach compared to the original. Motivated by professional workflows, our model, GazeShift takes as input an image and a mask demarcating an image region of interest and predicts parameters for a fixed set of global transformations to apply to the foreground and background regions of the image in order to shift visual attention, either towards or away from the masked region. Our encoder predicts global parametric transformations conditioned on the image and mask. This is done by concatenating the image with the mask and feeding this to a downsampling convolutional neural network. We reinforce the mask conditioning by applying the concatenation layer-wise throughout the convolutional part of the network. This is then fed to a series of fully connected layers via global average pooling. The foreground and background parameters are then predicted by two fully connected network heads. We use a sequence of fixed differentiable functions: sharpening, exposure, contrast, tone, and color adjustments, motivated by past work in computational photography. Our decoder then iteratively applies the predicted parameters in a fixed order to the foreground and background image regions demarcated by the mask. A hinge GAN loss during training maintains that the image transformations are realistic. An attention loss simultaneously attempts to maximize the saliency in the masked image region. The two losses compete to produce a final image that redirects observer attention while maintaining subtlety in the image edits. Let's take a look at some sample results. Consider this archival photo in this mask that selects the bus on the right side. Our approach successfully emphasizes the bus while maintaining fidelity to the input photograph. The result can now be used for workflows within design and marketing applications. Importantly, we can show that the edits applied successfully redirect visual attention. The predicted attention of the viewer, as measured by a state-of-the-art saliency model MDSEM, has been correctly redirected to the target image region. Here's another example where our automatically applied image edits redirect attention to the baseball player on the leftmost part of the image. Here's some more examples showing that our model can make both objects and people more attention-capturing, including the woman in white shorts, the house on the right, and the foal. Not only can our model automatically edit a photo, but compared to competing methods, it redirects viewer attention without generating artifacts or significantly deviating from the image semantics and the photographer's intention. Here's our results. Compared to results by Mehrez and colleagues on saliency-driven image manipulation, we see that their approach alters the semantics by recoloring whole objects and not maintaining faithfulness to the original photograph. Another model by Hagiwara and colleagues from 2011 modifies the background of the images so much that people can turn an unnatural hue and textures become distorted. The model by Matiscu and Bajic on attention retargeting by color manipulation frequently makes drastic and impractical photo edits. Finally, a recent method by Gatis and colleagues uses a generative adversarial network which generates serious artifacts in the output images. Using a set of user studies on 3 different datasets, we confirm that our approach successfully redirects human attention while maintaining high fidelity to the input image, whereas competing approaches trade off one for the other. Furthermore, because our approach is global parametric, it facilitates applications that are more difficult to achieve by prior approaches. For example, it can be easily extended with stochasticity to predict different parameter values. Here we produce outputs in different styles. We see different runs of our model in the skateboard, equestrian, and chef to make each of them more attention-capturing, but with different possible edits. We can also train our model to decrease attention with an extra pair of network heads and a tweak to the objective function. Here we see the rightmost boat becoming less attention capturing. This approach is useful for attenuating distractors in photographs. Our parametric approach allows our network to be run on lower resolution images that we can then apply the predicted parameters to high resolution photography. Here we seamlessly apply edits predicted at the image size of 240 by 320 pixels to the full resolution image of 1000 by 1500 pixels to direct attention to the backpack. Here edits are applied to this 946 by 1500 pixel image to make the leftmost beer glass more enticing compared to the original. The same reasoning can allow our transformations to be applied to videos. We predict parameters for the first frame and apply them to all successive frames that contain a common segmented object, such as the snowboard in this video. The left is the original and the right is the automatically edited result. Here we emphasize the parachute's backpack across all video frames. Finally, we can hand control back to the user and allow the user to adjust the level of edit applied. A user can tune the edits up or down by adjusting the relevant sliders. The interpolation takes place in parameter space and can happen at interactive rates. As the user adjusts the saliency slider, the sharpness, exposure, contrast, tone, and color curve parameters adjust accordingly, both for the foreground and background of the image. Individual parameters can also be adjusted to fix image edits and give users even more control over the parameters used and the final result. We encourage you to read the paper and explore the supplemental document for details about all of our experiments and plenty more examples of our approach in action. Thank you for listening.